Sinusoids can either lead or lag other sinusoids. So in this video, we're going to talk about how we compare sinusoids. Let's say we have two sinusoids, V sub 1 and V sub 2, each having a different or similar amplitude, the same angular frequency, but different phase angle. So I've drawn the two sinusoids here. So looking closely at the two sinusoids, we can state that V sub 1 lags V sub 2 by 30 degrees because V sub 1 crosses the horizontal axis 30 degrees after V sub 2 does. If we look at where the two sinusoids cross, or when the two sinusoids cross the horizontal axis, we will observe that V sub 2 crosses the horizontal axis first compared to the sinusoid V sub 1. And in fact, V sub 1 crosses the horizontal axis 30 degrees after V sub 2. So therefore, we can say that V sub 1 lags V sub 2 by 30 degrees because it crosses the horizontal axis 30 degrees after V sub 2 crosses that axis. Or conversely, we can also say that V sub 2 leads V sub 1 by 30 degrees because V sub 2 crosses the horizontal axis 30 degrees before V sub 1 crosses the same axis. Another way of comparing these two sinusoids is by plotting the sinusoids on a circular racetrack. So let's say we plot V sub 1 on the circle, and we plot it by first identifying the amount of uh, phase angle. So it's negative 75. So we plot uh, that sinusoid here as a small circle, and we assume that the small circle is um, revolving around or circling around that circle at the rate of omega radians per second. Next, we also plot the sinusoid V sub 2, and we see that it is plotted negative 45 degrees uh, from the horizontal, as shown here, and also circling the circle at the rate of omega radians per second. Note that since they have the same frequency or angular velocity, their distance will be a constant between them. Now, if we consider that these two sinusoids are running after the other, so in here we can see that V sub 1 is running after V sub 2, and it is clearly um, shown that V sub 2 leads V sub 1 by this amount of angle, so that's 30 degrees. Now there's another interpretation for this comparison, however, because we could also say that V sub 2 is leading, or V sub 1 is leading V sub 2 by this much angle, and V sub 2 is the one that is behind V sub 1 by this much angle. So we could also say that V sub 2 lags V sub 1 but this time by 330 degrees. So the question is, which is correct? Is this interpretation or this interpretation? Now, in comparing two sinusoids, who is leading or who is lagging, um, we always choose the smaller angle, which in this case is 30 degrees. So we don't compare it this way. So this is an incorrect comparison, and the correct way would be this one. So we choose the smaller angle uh, between the sinusoids. Let's have another scenario here. So let's say we move v sub 2 and change its phase angle by 45 degrees. So we plot it in our circular racetrack. So here is v sub 1, here's v sub 2, and clearly the angle, the smaller angle between them is 120 degrees. And so therefore we can conclude that v sub 2 is leading v sub 1, or v sub 1 is lagging v sub 2 by 120 degrees. Another scenario here, so again we move v sub 2, so v sub 1 is still maintained, so here's v sub 2, and we notice that their distance around the circular racetrack is 180 degrees. Now in this scenario, it's not clear which is actually leading or lagging between them. So when this is the case, we can say that uh, it is not clear who leads or lags, which sinusoid is leading or lagging which sinusoid. Another scenario would be if they have the same phase angle. So in this case, uh, neither one is leading or lagging the other. So the two sinusoids are said to be in phase. So sinusoids that are in phase reach their maxima and minima at the same time, and their amplitudes need not be the same. And lastly, let's say we have this scenario where the distance between them, the difference between their phase angles is 360 degrees. So in this case, we also consider these two sinusoids to be in phase with each other. Important note in comparing sinusoids in terms of leading or lagging sinusoids. So their angular velocity had to be the same. So that means they have the same frequency or the same period. Uh, if we compare them and draw them on a circle, they have to be expressed on as the same function. So it's either sine or a cosine. Now, the amount of leading or lagging between the two sinusoids will always be the smaller phase difference. Let's take an example. So we have here two sinusoids, I sub 1 and I sub 2. Each are expressed as the same cosine function, so we don't need to convert them to a sine function. And they have a different phase angle, so therefore these are not in phase sinusoids. So the question is which is leading and which is lagging, and by how much. So we draw it in a circle. So based on our drawing, it is clearly shown that I sub 2 is lagging I sub 1, or I sub 1 is leading I sub 2 by this angle. Here we have another example. let's say we have a sinusoid and we compare it to these three sinusoids and determine where when the sinusoid is leading or lagging these three sinusoids. Now for the first sinusoid, if we draw it in a circle, so take note, this sinusoid is in sine function, this one is also in sine function, so we can draw it directly on the circle. So let's say this is v sub 1 here, and this is v sub 2. So v sub 1 is 35, so it is somewhere here. Okay, so this is v sub 1, and v sub 2, this one is 35 degrees here, and v sub 2 is 120 degrees, so it is somewhere here. So here this is v sub 2, and this is 120 degrees, so this one is 35. So this one is 120, and the difference would be this one. So this would be the difference. That would be, well, that's 120 less 35. That should give us 85 degrees. So this should be 85 degrees. And we can say that v sub 1 lags v sub 2 by 85 degrees, or v sub 2 leads v sub 1 by 85 degrees. For the next two examples, since they are expressed in cosine, so we express this first in sine. So this is our sinusoids that needs to be compared. And if we draw that, so let's say we draw it, so this is v sub 1, and let's say we call this v sub 3, this is v sub 4 here. Okay, so let's compare, so let's say this is our circle. Okay, so again, let's plot v sub 1. So it's here, v sub 1, and this is 35 degrees here. This is 35. V sub 3 is positive 90, so it's somewhere here. So this is V sub 3. So this is 90 degrees. And V sub 4 is also located the same as V sub 1. So this is V sub 4. Okay. And because of that, we can say that V sub 1 is lagging V sub 3 by, so 90 minus 35, that will give us 55 degrees. So this one is 55. And V sub 1 is in phase with V sub 4 because they have the same phase angle after converting to a sine function. Okay, now let's go to the effective value of sinusoids. So we know sinusoid to be a periodic function that has an average of 0 over a single cycle. Now, so how do we measure the effectiveness of the sinusoid? So it is given here. Uh, it is simply equals to the its amplitude divided by square root of 2, or that would be 0.707 of the amplitude. So the effective value is just 70.7% of its maximum value. Now, the other name for an effective value of sinusoid is the what we call the root mean square, or RMS for short. Now, it is called that way because uh, let's say we have a sinusoid V. The RMS value is really computed as the a square root of the average of the integral of the square of the sinusoid. So that is a square there over one period. So we take the average of that. So we square the sinusoid, then get the integral from 0 to t, and then average that value over the period, and lastly take the square root of that. So that is what we mean by root mean square. So this is the root, the mean, and the square. So RMS. So here, for example, we have a sinusoid and we want to take the RMS value or the effective value. So we simply check what is the um amplitude, and we would get here, well, that would be 325 divided by square root of 2. Now for this one, now we have a negative sign here, so well, we can convert that into positive by um, simply adding 180 degrees to 60t. So that would be plus or minus 180 degrees. Okay, 180 degrees. So something like that. And again, we solve for the amplitude or the RMS this way. So there's no such thing as negative RMS. So in fact, if you're given this one, all you need to do is take the absolute value of the amplitude to get the effective value. So take note that the effective value depends simply on the amplitude. It doesn't matter what is the angular velocity or the phase of the sinusoid. So we just take the amplitude and we divide it by square root of uh, 2. Now, power utilities specify voltages by its RMS value. So, for example, in our household, in our homes, we see an outlet there. It is um, uh, it has a label there that looks like that, 230 volts, and we just don't label the outlet like this. So this is more appropriate labeling. Okay, so what is good about the RMS value, or what's the importance of the RMS value? So let's say I have here a resistance 100 ohms, and it is connected to a source with a sinusoid that is like this. And if you compute the RMS of this, that will give you 230 volts. And then let's say I have another circuit, but this time the 100 ohms is connected to a DC that is 230 volts. Um, that will give the same power for the 100 ohms. So, or in other words, the 100 ohms will actually consume the same power if we're going to compute it So the RMS value is likely its DC equivalent, and that it will give the same heating effect as a DC voltage that has a value the same as the RMS value of the sinusoid. So that's it for this video, and for the next video we will be talking about the response of basic circuits, AC circuits, to sinusoidal inputs. So we'll talk about series RL and series RC and series RLC, and derive the responses um, if these circuits are connected to sinusoidal excitations. So I'll see you in the next video.